I'll talk about the classification of SPT phases using an example, but there is some general result, how to reduce one difficult problem to another difficult problem, so to speak. So let me just show you some nice pictures I couldn't pass on. Just an introduction. The goal is to classify phases of matter, and these are different phases of water, and we know that crystal and liquid are different, but gas and liquid are the same in a certain sense. And here is the general idea why they are the same. On the phase diagram that includes two parameters, not just temperature but also pressure. One can go from liquid to vapor. And this will be taken as a basic definition. Two phases are considered equivalent if there is a connecting path without the phase transition. Now, if we want to show that there is no connecting path, then we have to use some invariants. And here are different problems that have no solution. This wheel is supposed to rotate by itself, but it won't because there is an invariant called energy. And and there is a different kind of invariant. I just use this example, the 15 puzzle. There are 15 pieces in this box and one empty place, and you can move these pieces in the box. And the problem is to switch two pieces. And you cannot do that because there is another invariant, which is the sign of a permutation defined along this line. And this is a discrete invariant. But we want to use something more interesting. We want to use topology as a way to construct invariants. And this is a visualization of the winding number of, or the degree of a map using a liquid crystal. In topology, we have discrete invariants of continuous objects. Now, let's start building our definition of equivalent phases or non-equivalent phases, and the type of systems we would hope to have a classification for, because obviously it's not possible in full generality. So this is one example. It's helium-3, and the phase diagram, this particular phase diagram involves three parameters: temperature, magnetic field, and pressure. In principle, we can have infinitely many parameters, and it is important that we want to allow arbitrary variations of parameters with some well-defined constraints. One constraint I'm going to use is that all those phases are restricted to zero temperature. And at zero temperature, this diagram is reduced to just two parameters, but in principle, one could add more parameters. One could change the potential of interaction between helium atoms, although nature just gives us one particular potential, but mathematically we can change many things. Why don't we want high temperature? Because many interesting phases can only be distinguished at zero temperature. If we go up in temperature and then go down in temperature, we could avoid a phase transition that occurs at this point. And two phases that are distinct zero temperature phases in the bigger phase diagram are connected by a path. It's like taking a piece out of the box. And we don't want to do that. Now, these are the rules of the game. We consider arbitrary Hamiltonians for fermions with local interactions at zero temperature. Another constraint that at zero temperature there must be a gapped ground state, meaning that any excitation has some constant energy relative to the ground state. We also use symmetry. One can consider systems without any symmetry constraint, but in this talk, the main example uses the time reversal symmetry. There will be no U1 symmetry, and therefore the particle number is not conserved. The particles are only conserved modulo 2. This is consistent with the helium-3 example, because helium-3 is superfluid at very low temperature, and effectively it means that particles can appear or disappear by 2 as they go into the condensate. Now, we disallow any usual order parameter like spontaneous symmetry breaking or topological ordering. Spontaneous symmetry breaking reduces the classification to the one without symmetry, essentially. And topological ordering, like in the Tori code or any system with anyons, just makes things too complicated, and I cannot solve such problems. Just I want to focus on systems without topological order. Such systems are called short-range entangled. And there are actually different definitions of things that are called short-range entangled. I'll use a particular definition which is different from Xiao-Gang Wen's definition. My definition is this. If we have a short-range entangled phase, by itself it may not be connected to the trivial phase. By trivial I mean a product state. Each spin in the system points up, or the electrons on the lattice are localized or something like that. It's there is a class of states that may be called trivial. So it's not required that a given state is connected to the trivial state by a continuous path within this requirement, within the space of gapped ground states. However, it is required that there is another system such that when we take two together, we can find the connecting path. So for any short-range entangled state, there is an anti-state such that the two together cancel each other and they become trivial. And an example would be integer quantum Hall effect with nu equals 1. We can cancel it with another quantum Hall layer with nu equal to -1. If we turn electron tunneling on and crank it up, eventually the electron tunneling between the two layers will drive the system to a state that is very close to the trivial one, and then we can turn off the kinetic energy of electrons. And this way we cancel the two systems with integer quantum Hall effect and continuously go to a product state. So this is the notion of a simple or short-range entangled phase. And now...
Can you explain the terminology? Short-range entangled? We call that having an inverse short-range entangled.
Well, I have some intuition that it means something about entanglement, this condition that we can cancel. However, I don't think it, I can explain it very well. Well, if we have a system with anyons, and this system is put on a torus, for example, then one can see that there is a long-range entanglement because we can cut different annular shape regions around the torus. And if the quantum state on the torus is a superposition of labels along the given direction, the torus is just a cylinder that is closed up, and we take two ribbons around the cylinder in two different places, and the state is a superposition of different labels on along the main direction of the cylinder. Then these two ribbons will be entangled, and that happens at arbitrary long distance. This adds a lot of complexity to the problem, and I'm trying to avoid that complexity.
Another question regarding this
Yeah.
definition. So when you said the formal definition of having an inverse or having short-range entanglement,
Yeah.
Well, originally it had a symmetry. Question is, suppose you do not define, the same notion without symmetry. Well, but the original system happens to be symmetric. Is it still short-range entangled with respect to the once symmetry is taken into account? That is, if a system has an inverse without regard to symmetry, inverse with symmetry.
That's a good question. It follows from the results. I'm going to show that it is true that if the system is short-range entangled without symmetry, and it is symmetric, then it has an inverse with symmetry. But I don't see how to prove it directly. Okay. I want to describe a class of Hamiltonians that have easy solution, and at the same time to introduce some formalism for more general Hamiltonians. This is an easy Hamiltonian. It's quadratic in the creation and annihilation apparatus of electrons or of helium-free atoms. If we replace those creation and annihilation apparatus by these operators, they're called Majorana apparatus, and they satisfy some simple commutation relations, then the Hamiltonian is just a quadratic form. It's actually given by a skew-symmetric real matrix A, because those apparatus anti-commute with each other. So a quadratic Hamiltonian in general has this form in the Majorana apparatus. And one can in principle consider a quartic Hamiltonian or a higher order Hamiltonian. Let's see how they're different. Actually, we'll see it a little bit later. This is the Majorana formalism for continuous systems. And I write the Hamiltonian in this form. There is a continuous Majorana field eta, which is a multi-component vector depending on the position in space. And the Hamiltonian is similar to the Dirac operator. It's not technically it's not a Dirac operator, but it has some first-order derivative terms, gamma matrix, gamma mu times d mu, plus a term without derivatives, the mass term. And in principle, those gammas and the mass term can be arbitrary, or we can add second-order terms and so on. However, the point is that any Hamiltonian can be continuously deformed to a special Hamiltonian of this form without closing the energy gap. So, yes.
You mean in arbitrary topological space can be sphere, torus, and things like that.
Yeah.
So even when the space is arbitrary topology, you can do that in the corresponding topology.
This mass term will depend on the position. But
think about the closed space, so there's no boundary, so one don't need to worry about the gapless boundary.
Here
the issue whether this can be done sphere or this can be done on any topological space.
It can be done on any nice topological space. It can be embedded, okay, let me define a nice space. It can be embedded into Rn. N is some large number with a tubular neighborhood.
Does that include lattices?
This model is a continuum model, but there is another result, that any Hamiltonian on a lattice with local hopping terms given by this matrix A can be reduced to a Hamiltonian of that form, in the sense that the topology of the two types of Hamiltonians is exactly the same. It doesn't mean that the
How do you compare?
how do I compare? There are two maps. There are two spaces of Hamiltonians. Some Hamiltonians are not nice. Say they are gapless. If we consider gapped quadratic Hamiltonian, and there is a notion of a local gap, when the hopping matrix is local, in principle, when we diagonalize the matrix, we get eigenvalues, but an eigenvalue is a non-local notion. At least for quadratic for Hamiltonians, there is a notion of a local gap. So suppose we have we consider all locally gapped local Hamiltonians on a lattice, and similarly all locally gapped local Hamiltonians of that form, which are continuous. Then each continuous Hamiltonian can be discretized, put on a lattice, like we used to define a difference method for PDEs in this sense. So we just take a fine grid and define this differential operator. We approximate the differential operator by a difference operator on the grid. And in the other direction, if we have a lattice Hamiltonian, it's more complicated. I cannot describe it very easily, but the rough idea is that when we have a lattice and all correlations are local, around each point, we only care about a neighborhood, say, of radius 10 in terms of the lattice distances. And now we can have, say, 100 sites that we care about. We introduce auxiliary fields at 100 of them. Actually, the size of this disk or a ball around the given point times 2 to the n, where n is the dimension. We introduce that many auxiliary fields, and there is an explicit construction how to turn a lattice Hamiltonian into a continuous Hamiltonian.
Understand that, but my question is more of how you imagine comparing two Hamiltonians which act on different Hilbert spaces, unless you make an identification between these Hilbert spaces. So maybe you've already answered my question.
Well, the philosophy is this. We consider the space of Hamiltonians or the space of ground states as a topological space. And I'm not saying that these are the same Hamiltonians, because they act on completely different degrees of freedom. I'm saying that the homotopy type of the space of all possible Hamiltonians on a lattice is the same as the homotopy type of all possible Hamiltonians of that form. So the spaces of Hamiltonians are homotopy equivalent. I'm not saying anything about the physical meaning. It's just a formal construction. And here is an example of the correspondence in the easy direction. If we have a Majorana chain, it's a discrete Hamiltonian, However, assuming that the parameters are in a certain range, u and v are close to each other, both close to 1, we can write a continuous Hamiltonian that is similar to that Hamiltonian in some sense. This is just an illustration. It doesn't show that such a correspondence always exists. And here is the full classification of Hamiltonians at dimension 0. Here there is no notion of continuity. It's just one blob that consists of, say, 100 lattice sites. An electron can hop between any two lattice sites, and there is a 100 by 100 matrix. We just classify all such matrices. And actually, we do a stable classification. The dimension of the matrix is not fixed. We are allowed to add extra blocks to this matrix and use these extra blocks to find a connecting path. So we're doing some kind of stable classification. And the stable classification means this. We start with the unstable version, and here is the space of matrices up to homotopy. Because this Hamiltonian, given by matrix M, has eigenvalues plus or minus 1. A physical Hamiltonian may have arbitrary eigenvalues, but with an energy gap. And we can deform the Hamiltonian continuously so that to make the eigenvalues to be plus or minus 1, then we get this space. It's the space of all such matrices. And then I say classifying space, technically it's not the correct term, but anyway, I mean the stabilized version of that. We take M to infinity and we come up with this result. The space of Hamiltonians is homotopy equivalent to O divided by U in dimension 0. And this space has two connected components. They're distinguished by the phi-fin of the matrix M. And physically, the phi-fin means whether there is an even number of particles or an odd number of particles in the ground state. So this is not just a property of the Hamiltonian, but actually a property of the ground state. The Hamiltonian is just a tool to stabilize the ground state. In all dimensions, we get Bott periodicity. In each dimension n, we have the corresponding space of Hamiltonians up to homotopy. And these are the 8 relevant Hamiltonians. Here we are not imposing symmetry. If we impose symmetry, then there are two more possibilities.
How that is different from 10-fold way?
It's the 8-fold way. It's the Bott periodicity in the real K-theory. And the other two cases, the complex cases, occur if we impose a U1 symmetry. It's for consort particle number. Now, we can add different symmetries, like the time reversal symmetry. And in the world of quadratic Hamiltonians, symmetries should be linear. So the time reversal symmetry is just the linear transformation of the Majorana apparatus. And this linear transformation is described by a matrix T. There is this curly T, which is an operator, and just ordinary capital T, which is a matrix. And this is an example of such a matrix. This particular matrix squares to -1. In principle, it could square to +1, but such systems are not realized in nature. Theoretically, we can consider both types of systems. And finally, this is the application to 3D superconductors with time reversal symmetry. So the Hamiltonian has this form with 3 gamma matrices and a mass term, and the mass term is required to anti-commute with the gamma matrices, and that fixes the form of the mass term. It is this form. I just picked arbitrary gamma matrices that anti-commute with each other. Just wrote them in a basis. It's not so important which basis to pick, it's just a convenient basis. And the time reversal symmetry described by a matrix T that also anti-commutes with the gamma matrices and with M. And the requirement that the Hamiltonian is invariant under the time reversal eliminates this term, and we're left with that term. So the mass term has a special form. It's a real symmetric matrix with plus minus 1 eigenvalues. This little m. Capital M is skew-symmetric, but the little m is real symmetric matrix. And it has a topological invariant, which is this, the number of plus eigenvalues minus the number of minus 1 eigenvalues. The signature of this matrix is a topological invariant. And here is the main question. Is this invariant nu well defined in the presence of interaction? In other words, can a nu equal to 0 state be continuously changed into a non-trivial state such that the intermediate states may include interparticle interactions, but the energy gap must never close? This is the question I want to address. And the answer is this. Nu is defined by defined modulus 16 in the presence of interaction, meaning that if there are two numbers, nu and nu prime, and they differ by a multiple of 16, then we can find a connecting path. Otherwise, we can't.
Alexei?
Yes.
Is 16 related to Rabi error?
I don't know. I don't know. So let me just describe how the problem is solved. Maybe somebody can recognize whether it is related or not. First, when we consider nu equals 0 and nu equals 16, there is an explicit construction. I'll just show the connecting path. If nu is not 16, then the problem is more difficult because we need to consider all possible quantum states and prove that no connecting path exists. And later on, I'll give some idea how to type this set of states. They're described as cross sections of a certain fiber bundle over the classifying space of the symmetry group. The symmetry is Z2, the classifying space is RP infinity. So we consider certain fiber bundles over RP infinity indexed by an integer, and we ask whether two bundles are fiber-wise homotopy equivalent. And this problem is solved using homotopy theory, obviously, namely a T-Herzbruch spectral sequence. And this confirms the previous answer. For example, one can show that nu equals 0 and nu equals 8 are not connected by a path.
Are you going to define nu for interaction systems?
How do I define nu for interaction systems?
So far, just defined for free.
Right. So the endpoints have a certain value of nu. These are non-interacting systems. The connecting path, in principle, doesn't have a definition of nu. So we don't define nu for interacting systems. And I want to take a short break for a discussion, but first let me acknowledge the contribution of other people. John Morgan helped me with this homotopy-theoretic calculation, and we hope eventually to write some joint paper on this subject. We did some calculations together. Unfortunately, it hasn't come up yet. I have been very slow on this problem. And I also want to thank Ashwin Vishwanath and Shanyan Chi for inspiring discussions, and Michael Friedman and Dennis Sullivan for teaching me some mathematics that will be used, like classifying spaces and homotopy fixed points. Okay, and do you have questions at this point before the technical part? Yeah.
So for this implying fermion system, do we need to consider addition of this fermion number conservation model Z2? Do we need when you consider global symmetry to include that information?
Right. In principle, we consider it implicitly. The thing is that we cannot even imagine a Hamiltonian that does not conserve the number of fermions modulo 2. I mean, there is no way to write such a Hamiltonian. If we add odd terms in that Hamiltonian, different terms far away will anti-commute with each other, and this doesn't make sense. But I consider the fermionic world and the bosonic world as different worlds. So there are two separate problems that need to be solved individually.
How do you get the group structure on pi 0 of the homogeneous space that you wrote just now?
Oh, right.
How does it correspond to the physical notion which you were describing just now in order to add things in some notion of GPS?
Sure. Suppose we have two elements of pi 0, which are two topological faces, say, on a plane, and we stack those planes together. Now, these are two parallel planes, and this is a new system which is characterized by a certain element of pi 0. This is the notion of addition, and this cancellation property means that there is also subtraction, and it means that pi 0 is actually an abelian group. Yeah. Okay. You can always say that topological faces form an abelian semigroup just by sticking together. It's
on the physical side, but I mean, there are two connected components that you were saying. So, how do you take one element each? How do you put these connected components?
Well, connected components of what? Of what space?
Your U over O.
Oh, U over O? You take the direct product of two vector spaces and consider block diagonal matrices like A, 0, 0, B. And you get a matrix that is bigger than the original matrices. But the construction is stabilized. It's defined as a direct limit of things for each fixed matrix size. And in this direct limit, this operation is well defined. So when we consider matrices of dimension 4, for example, we have two matrices, A and B, of dimension 4. They correspond to A block and the identity block in dimension 8, and identity and B also in dimension 8. And the sum of A and B will correspond to A and B on the diagonal in dimension 8. Okay, shall we move on?
Sure.
So let me consider a related but somewhat simpler question. This is a physical problem. Suppose we have this topological superconductor in dimension 3, and it has some non-trivial value of nu, and we consider the boundary between this topological superconductor in vacuum, which is nu equals 0. And we can formulate an effective boundary theory that doesn't have any mass term. It's just first order terms. This is the effective Hamiltonian on the boundary, and this whole box is the boundary of a topological superconductor. It's the top view of that boundary. Oh no! Actually, the boundary in this picture I meant the boundary to be this green line. So there is nu equals 1, nu equals nu 2. Just this green line. And at the boundary, we may introduce possible mass terms of this form, such that anti-commute with the gamma matrices. And M is a real symmetric nu by nu matrix. If we add such a mass term, then the Hamiltonian becomes gapped. This one is gapless. Unfortunately, this capital M breaks the time reversal symmetry, because tau of M equals to minus M. And I'm using this parameterization with little m just for convenience. So there is no way we can add a mass term such that does not break symmetry, the time reversal symmetry. The hope is that we can add some more complicated interactions, say a quartic term or a sixth order term or some high order term that would preserve the time reversal symmetry and still open a gap. So how do I achieve that? This is the general scheme. It's a dynamic surface mass term. The key idea is this. Let the mass term be a function of the coordinate on the surface and time. And this function fluctuates. It's a Bose field. Our system is built out of fermions, but we're adding a boson. In principle, one can build bosons out of fermions if we really want, but let me just say it's an additional degree of freedom. And this additional degree of freedom will aid the construction of the Hamiltonian. So the rough idea is that there's bosons, or this function m of x and t, changes slowly in space and time. And this function defines some effective potential for the fermions that are fast. So the process is adiabatic for the fermions. And for each configuration of the mass term, we have a gapped state of fermions, but the fluctuations of this function m by themselves may be gapless. And we need to make sure that those fluctuations are actually gapped. And this is a non-trivial problem. Let's think about possible abstractions, why the fluctuations may not be gapped. One possible abstraction is this. Suppose we have two regions with positive m and with negative m. If we just have one region, it's not good because the time reversal symmetry is broken. If we have both, there is a boundary between these two regions, And depending on the particular circumstances, there may or may not be a gapless mode at this domain wall. Now, if M is just a number, it's a scalar rather than a matrix, then indeed there is no continuous path between positive M and negative M that would not cross zero. As soon as it crosses zero, it means that the fermions become gapless at this band, right? And this construction doesn't work. And in fact, for nu equals 1, this is bound to happen. For nu equals 1, we don't have enough freedom to avoid this domain wall. However, when nu equals 2, we can have M, it's a mass term, which is proportional to sigma z, this sigma z. And if we apply the time reversal symmetry, it's minus sigma z. Now, there is a connecting path. We can continuously connect sigma z through sigma x to minus sigma z using this variable theta. So there is a path P1 in the space of 2 by 2 matrices. And we have avoided this basic abstraction or domain wall, but we might still have high abstractions. This is a possibility. If we take this path P1 and apply the time reversal symmetry, we get another path, T of P1. And imagine that this whole loop is not contractible. If we construct a configuration in the real space where going around this circle corresponds to this loop, each point on this circle is mapped to a point of that loop, then in the middle there will be a gapless vortex, like in a P plus IP superconductor. So this is not good, and such situation occurs when nu equals 2. Now things become a little fuzzy. If this abstraction occurs, there is no immediate proof that we cannot make a gapped state, and we need a separate argument. However, if this abstraction does not occur, this is good. We can proceed, and eventually we'll construct a gapped ground state or a gapped Hamiltonian. So we need additional steps. When nu equals 2, the abstraction is gone, but there is another possibility of a soft core soliton. It's not a vortex, but a continuous texture. It's also called a fermion on the boundary of this 3D superconductor that carries an additional fermion. So it's a kind of lump of fermionic density. And if you integrate this fermionic density, it's an additional fermion. And this also creates a problem with making a superposition of different field configurations, because some configurations will have fermions, some will not have fermions, and we cannot construct a superposition between them. But if this soft core soliton does not occur, then we are in a good shape and we can go further. So for nu equals 8, no soft core soliton, which is good. And we write the mass term in this form. There are coefficients UK that depends on x and t, and some basis matrices M sub k. There are 4 basis matrices, and the order parameter is a sphere, and we call this sigma model with the target space S3. Now, this sigma model can be defined in field theory. It will have some dynamics. The question is whether this dynamics is gapless or gapped. And if there is a non-trivial Wessels-Wiener-Witten term in the dynamics, then it's not obvious, but we cannot anyway. We cannot easily prove. It's not obvious that it is gapless, but in fact it is gapless. But we can easily prove the other thing. If there is no Wessels-Wiener-Witten term, which happens when u equals 16, then the ground state of this sigma model is gapped. Again, it's also not completely obvious, and in the end I'll show you an explicit construction on a lattice. So it still requires a proof, but at least it's something conceivable. Yeah.
You don't say not for Wessels-Wiener term. Do you have a symmetry like SO3 symmetry? Or
No, no.
I see. So that's the reason why it's hard to argue. I think if you have a symmetry, then you need the calculus. That's because you have Wessels-Wiener term, but you don't have a symmetry, so it's hard to say.
Well, I have an actual proof, so. But I won't show it today. I'll just give a general scheme because this requires solving this spectral sequence. Yeah.
You might explain why the tiny space in the when A's case is different. So if you use this Wessels-Wiener-Witten term, what is as D sphere, D is related to space-time dimension like D plus 2.
Mm-hmm.
But your case is S3 and S5. In these two cases, I wonder if there is a reason
the target space is S3, and the space-time is the target space is S3. Just a second. And we're in 2+1 dimensions because we're doing the boundary theory.
Also, the last noise actually doesn't work.
This is a homotopy-theoretic argument. I'll show you this argument in the end. So roughly, the logic is this: there may be some non-trivial term like the Wessels-Wiener-Witten term, but we cancel it by a local counter term. And to show that this local counter term exists, we take this extension to higher dimension and do some mathematical construction and define a term that entirely in terms of S3. So technically, we extend to S5, use a certain form, integrate it over S5, do something, and then restrict back to S3. The actual model is defined on S3.
Which dimensions? How many dimensions does the model live in?
2+1.
But the Wessels-Wiener term should be in the 3+1. So I wonder, in order to define Wessels-Wiener term, I would go one higher dimension. So do you think that the mapping from S4 is non-trivial Wessels-Wiener term?
Why?
Because the theory is a 2+1, but the Wessels-Wiener term of 2+1 is a kind of a 4 dimension. It's one higher dimension.
The Wessels-Wiener-Witten term is an integral of some form over 4 dimensions.
Yeah, but the thing is, if the target space S3, whether do you have a Wessels-Wiener term? Oh, because of the mapping from that. Are you using the mapping from S4 to S3? There's not trivial.
High for S3 is D2. So
That's a
Just a second. Well, maybe I'm using wrong terminology. I think it's still correct.
There's a sigma to WZW term with S3. That's correct.
Yeah.
That's good.
Mm-hmm. So to show that the nu equals 8 phase is non-trivial, I'll just describe the steps. And the problem is this. When we go step by step, we basically double the previous step. We constructed some solution for nu equals 4. It doesn't work in high dimensions. There is an abstraction. To avoid abstraction, we double this, get nu equals 8, and then there is a particular way to extend the map to a higher sphere. However, if at some previous step we did something different, the situation at the next step might be different also. And in that case, it's conceivable that the abstraction would vanish. And to show that the abstraction does not actually vanish, we need to do the full homotopy theory. We need to construct this space, RP infinity, and consider a certain vibration. I'll describe that in a moment. And use some algebraic tools, which I won't mention, but the end result is this, that these two cases are different. They are not connected by a path. Now, this is the general claim. All the previous stuff is a special case of this implication. If we have a complete classification of short-range entangled states in some dimension, say in dimension 2 or dimension 3, then we automatically have the classification of SPT phases in the same dimension. But there is a catch. We need a complete classification, which means the following. We fix dimension n and consider the topological space of all possible short-range entangled states. It's not just answering the question whether there are non-trivial phases or not. It's also computing homotopy groups of that space of Hamiltonians. So if the space of Hamiltonians has a non-trivial homotopy, then the answer is still non-trivial. And this is something very simple. If we just consider bosons in 0 dimensions, then the space of all possible quantum states is CP infinity, because quantum is the vector in some Hilbert space of an overall phase. And it's this space that parameterizes such vectors. And with fermions, there is an additional invariant, the fermionic parity. It's the answer up to homotopy. It can be CPN plus CPM, but in the limit, it can be identified with that.
So before we classify Hamiltonians, now we're classifying states.
Right. When we consider different Hamiltonians for the same state, such that all these Hamiltonians are gapped, and that given state is the ground state of each Hamiltonian, then the space of such Hamiltonians is contractible, because we can continuously interpolate between two gapped Hamiltonians, and the gap is still preserved. It means that the topology, or the homotopy type, of the space of Hamiltonians is the same as for their ground states. So these spaces are also known at dimensions 1 and 2. Yeah.
You started talking about these short-range entangled states at the start.
Yeah.
You switched to this question of fluctuating mass terms for fermions.
Right.
Is there some argument that, whatever short-range entangled state you write down would be some fluctuating mass term, or perhaps there's some completely other way of constructing it?
Some fluctuating mass term?
Well, you were writing down these states with these promoting the mass terms in a fluctuating field. This was, and perhaps there are some other short-range entangled states.
probably. I don't know. It's an incomplete construction. On the next slide, I show why it is sufficient to consider fluctuating mass terms, roughly. But it's conceivable that just fluctuating free fermionic Hamiltonians will not give us the full picture, especially in high dimensions. This is an important property that the sequence of BNs or the sequence of FNs is a homotopy spectrum, meaning that each space is the loop space of the next space in one dimension higher. And there is a simple physical interpretation. If we have a topological phase in dimension n, say in dimension 2, it can be realized as a soliton in dimension 3. And again, if we have a path in the space of three-dimensional phases that begins and ends at the trivial phase, we can consider a three-dimensional configuration where the state on the left is trivial, the state on the right is trivial, and in between there is a continuous transition according to that path. And then there is a two-dimensional slab of non-trivial material, which we just consider with respect to those two dimensions and ignore the perpendicular direction. So there are maps between textures in dimension n+1 and just ordinary states in dimension n. And to construct a soliton in n+1 dimensions out of a state in n dimensions, we must use this constellation property. In general, it won't work. If we have, say, a toric cohort or fractional quantum Hall effect, we cannot realize it as a soliton in a four-dimensional, in a three-dimensional system. Continuous as a continuous soliton. Now, the answer is this. If we know the spectrum, then the SPT with symmetry group G are classified by generalized cohomology in that spectrum. For the time reversal symmetry, unfortunately, it's complicated. We need a twisted version. And this answer is a generalization of some known approximations. There is a classification of bosonic or spin systems using ordinary group cohomology. And this approximation boils down to the existence of a map. There is a map from KZ n+2, the Eilenberg-MacLane space, to that unknown space Bn. Although the space is unknown, this map can be constructed. And therefore, there is a map between the cohomology groups. And this H upper n of Bg with integer coefficients is an approximation to the actual classification. And for fermions, there is another space, not KZ n+2, but it's a spectrum with two non-trivial homotopy groups, and it was considered by Dan Fried. You would just use this spectrum as an approximation to Fn. We get something that was termed supercohomology. Yeah.
It is B and F are building groups because we don't do the H. And BGB, that B should be a building group.
This one? Yeah, it is an abelian group.
So
Yeah.
B is a building group.
B is not a group. It's a space. BG. The coefficient is also a topological space.
Okay. But do you require this coefficient of some abelian you can have act?
No, there is a construction in homotopy theory called generalized cohomology, and usually we consider cohomology with coefficients in an abelian group, and they can be described topologically as maps from the space we want to know the cohomology of to the Eilenberg-MacLane space. So in this case, the coefficients are in the Eilenberg-MacLane space, but this is a generalization. This one. Now, I want to answer Matt Hastings' question. Why we can just consider fluctuating mass terms? This is special to the three-dimensional classification, and let's collect the known information about F3, and we start with free fermions. Free fermions correspond to mass terms satisfying some constraints. There is a map from F3 for free fermions to the actual F3. And all the homotopy groups of free fermions are known, and they actually go to infinity, and there is a periodic pattern with period 8. The homotopy groups of the actual space end up here. Pi 5 is the last non-trivial homotopy group. All the rest is 0. However,
Why?
Because it is a spectrum, and calculating, say, the fifth homotopy group for that space is the same as calculating the fourth homotopy group of the loop space. And when we consider loops, two-dimensional loops, three-dimensional loops, we reduce the effective dimension. And as we go to this point, we have reduced our calculation to this case. And eventually we see pi 2 of CP infinity, which is the same as pi 5 of F3. And CP infinity doesn't have high homotopy groups. Okay, now these numbers are obtained by some non-rigorous argument. These two numbers are completely rigorous, Z and Z2. That one is also rigorous, and it follows from Matt Hastings' result about one-dimensional phases. That any one-dimensional gapped state can be approximated by a matrix product state, and for matrix product states we can have a full classification. So this way we have information up to here. This Z is the chiral central charge of two-dimensional systems. So each number here corresponds to pi 0 in a certain dimension. This is pi 0 in dimension 0, this is pi 0 in dimension 1, and that is pi 0 in dimension 2. And physicists have studied two-dimensional systems to death, which doesn't mean that they're not missing anything, but I feel it's unlikely to find new phases in 2 dimensions. Again, it's not a rigorous argument at all. And in dimension 3, in dimension 3, I won't even guess what the answer is. I just don't know.
So there's no new phase in the sense that you can consider this kind of invertible TQFT. It's kind of short-range interval state in your definition. So I mean, like this, if you have a lot of ground state degeneracy.
Yeah, if we allow ground state degeneracy, of course, there are more phases. However, if we focus on the question whether two different free fermion phases are connected to each other, we're restricted to one connected component of F3. And given this table, we can reconstruct the homotopy type of that connected component. It's SP over U restricted to dimension 5. It's a Postnikov space of SP over U. SP over U is that space. So we know the connected component.
Alexei, could you explain why you know so much about F3? I mean, all the numerology that what you just explained has to do with starting with F3, right?
Yeah.
How is it that you know F3 is SP over U, but you don't know the other FIs?
Free
part?
Yeah, the free part is completely known. Then there is this map that is an isomorphism on the homotopy groups up to here, and then it vanishes.
Okay, but maybe you could explain the numerology. I mean, so dimension 0 corresponds to three-dimensional fermionic systems. Dimension 1, two-dimensional. There's some, the two dimensions add up to 3, right? I mean, yes. But why 3? I mean, where did that come from in this classification?
Why using this number 3 here? Because our original problem is three-dimensional.
Oh, I see. Okay. You're specializing.
Yeah.
Okay.
Yeah.
Is that's the world we live in or something? It's because it's content.
Yeah. Well, I picked a particular example. Yeah.
What is the Z doing in degree 5? Shouldn't that be something like negative 2-dimensional?
Yeah, it's negative 2-dimensional. Yeah, let's go back. Z in degree 5 in this is the same as Z in degree 2 for that space. And indeed, CP infinity has a non-trivial pi 2.
I guess it's just disturbing that these are not connected. What can it physically mean?
Pi 2. This pi 2 is the Berry phase, Berry curvature. So there is a form that integrates to 1 or 2 pi on a non-trivial 2 loop, and that form is the Berry curvature. That's the physical meaning. So now we consider fixed points of the symmetry group. And this is a cartoon. We have F3 free, and those ellipses are sets of fixed points or connected components of this set of fixed points. And they're mapped to connected components of the set of fixed points here in F3. And there is something that we don't know. There are other phases, but we are just focusing on one connected component of F3, and within that connected component, we want to identify fixed points in their connected components. How do we reduce the problem of fixed points to homotopy theory? That's the key idea, that somehow calculating fixed points can be reduced to pure homotopy theory. A priori, it might not work. And this is a very basic example. Consider some group G and consider its action on EG. EG is part of this fiber bundle. EG is the total space of this bundle over BG. And it acts on the group acts on EG without fixed points by definition. And it also acts on a single point, and when it acts on a single point, there is one fixed point. One fixed point. But these two things are homotopy equivalent. So ordinary homotopy theory cannot tell these two cases apart. We need equivariant homotopy theory to distinguish them in general. However, there is something very special about interacting fermions, so interacting bosons, not free bosons, or not free fermions. There are fixed points and there are homotopy fixed points. Each fixed point is automatically a homotopy fixed point. There is an inverse map that is well defined for interacting fermions, so interacting bosons. And this is a definition of a homotopy fixed point. A homotopy fixed point in an arbitrary space X with an action of group G is a G equivariant map from EG to X. So a G equivariant map from a point to X would be just a fixed point. And we're replacing the point by EG. And what do we gain from that? Well, we actually lose some information by considering maps from EG to X. However, one can take this equivariant map from EG to X and eliminate the symmetry entirely. We can pass to this space. We do the Borel construction, multiply by EG, and then take the quotient over G. And there is a fiber bundle from that space X tilde to BG, whose fiber is X. And each homotopy fixed point describes a section of that fiber bundle. And vice versa. Each cross-section of that fiber bundle is a homotopy fixed point. Yeah.
You're going to explain the map from homotopy fixed points to fixed points?
I'll try if I have time. It's already late. Yeah. Okay. So this is how we do it in principle. Take a homotopy fixed point. We try to define a G invariant quantum state, which would be an actual fixed point. And it is defined this way. It's a uniform superposition over all maps from Rn to EG. It's a fluctuating order parameter. It's a sigma model with the target space EG. And we integrate over all configurations of the order parameter. And for each configuration M, we take the state of free fermions given by that local description. Near each point in space, we calculate the value of M of X, which is an element of EG. Apply function F, we get an element of Fn, which is a fermionic Hamiltonian, and we require that our state looks like the ground state of that Hamiltonian near that given point X. This is the description of this state psi. And we want to define the state as the ground state of some local Hamiltonian 2. But there are two issues. One issue is that the integral is too big over, we cannot possibly integrate over all functions, all continuous functions like that. We need to do something, need some cutoff. And another problem has to do with phase factors. How do we pick the phase factor in front of that? Here is the solution to the cutoff problem. Instead of saying that there is a fluctuating continuous order parameter, there are spins on a lattice. Each spin takes values in the group G. And then out of those spins, we define just theoretically a function on the whole plane or on the whole Rn, which would work as a mass term for fermions or some local constraint for fermions that would play the same role as the continuous order parameter m. And to define such a function, we use Milnor's model of EG. I recall Michael taught me this thing, and it was very difficult to me to understand what that thing is. It's an infinite join, so don't worry if it looks unfamiliar. But for those who actually know this thing, when we have a join of k plus 1 copies of G, then this space is k minus 1 connected. And also by construction on the join, given a simplex, an n simplex, and group elements assigned to the vertices of that simplex, we have a map from the simplex to xn. That is basically how this xn is defined. Now, imagine we have a spin configuration on all the vertices. For each simplex, we have a local map from delta to xn. And by patching those maps together, we get a map from the whole plane to xn. And xn is a subset of EG because we can embed xk into EG. And finally, the state is structured this way. It's a superposition of all configurations of spins on the lattice, tensor the fermionic state defined by the composition of the two maps.
So where do you put the fermion in this construction?
The fermions are in between. The fermions are continuous.
Oh, I see.
But you can approximate them by discrete fermions on a much finer lattice. There is a coarse lattice for this group spins. So this is issue number 1 solved, and issue number 2, phase factors. So suppose we have two configurations of the order parameter, m prime and m, and it does make sense to talk about the absolute phase, but the relative phase is well defined. And we construct a Hamiltonian that would move those configurations one to another adiabatically, and they would be connected by an adiabatic evolution operator U that depends on a path between the two configurations. Now, we can just say that this adiabatic evolution takes one fermionic state to the other. Then it's easy. We can implement this Hamiltonian on a lattice in space-time, and we can just use the previous construction with xn plus 1 instead of xn, and using this space-time, we need an n plus 1 simplex to allow a spin flip. And when a spin flips, the fermions follow adiabatically. However, there is a new problem. Suppose there are two different paths or two different spin flip patterns between two configurations, m and m prime. When we go along one path and along the other path, we get different phase factors. The phase is different by that number. So we really need to make sure that this factor vanishes. And to do that, we will modify the adiabatic evolution operator by a local counter term. And to this end, we first observe that our target space has trivial pi n plus 1. Therefore, between each pair of paths, there is a high-dimensional surface. And we can obtain this buried phase by integrating the Berry curvature along this high-dimensional surface. So the Berry curvature comes from some universal n+2 form on the space of Hamiltonians or quantum states itself. We know that the usual Berry curvature is a 2 form on the space of zero-dimensional Hamiltonians. If we have Hamiltonians on a lattice in some dimension, we can define an n+2 form. And it's universal. It's just made of quantum mechanics, so to speak. Then we take the pullback by function f, and we get a form on EG, and another pullback by this surface, and we get a function on this space. It has Rn, the physical space. One parameter is along this path, and the second parameter in here is in the vertical direction, between the paths. And it looks like a WZW action. However, the target space is contractible, therefore we can trivialize that action. We integrate this form on the contractible space and get a form little omega. And then we average it over the group and make it invariant. And finally, we integrate that form over a path and add this integral as a counter term to the natural adiabatic evolution. This overall evolution with this extra phase factor satisfies the right condition. So those phase factors are killed. And here is the conclusion. So the classification of SPT phases splits into 2 subproblems. First, we need to find these spaces, and they are known in dimension 0, 1, sort of known in dimension 2, and completely unknown in high dimensions. So this is a really interesting problem. The other problem is less interesting because, well, there are people who can solve such problems easily. I'm not one of them. I solved one instance of the problem with some help from John Morgan, and I cannot solve more complex instances of that problem. It requires some advanced spectral sequence calculations. But in principle, this technique has been developed by topologists. So
how are you supposed to solve a twisted general cohomology if you don't even know what the spaces are?
Well, in low dimensions, we do know.
You've only done a part 2 in low dimensions.
Yeah.
You also have physical arguments, not just for the homotopy groups, but for the K invariants, how they're connected. I mean, the calculation depends on those.
This calculation shows the homotopy equivalence between the set of fixed points and homotopy fixed points. There is one subtlety here. When we integrate the form, we make an arbitrary choice, but it turns out to be relevant to this problem.
No, but the spectrum F, I mean, I guess you're assuming the map from the free one in that range is an equivalence, basically.
Oh, the spectral F has K invariance. Yeah,
Right.
it does.
But do you have physical argument for what they are, or you're just
Yes.
assuming the map from the free one?
Well, I'm assuming the map, and I know what these invariants are for the free case.
Yeah, okay. So you're
Yeah.
getting it from the free
Yeah.
case. Okay.
Well, let's ask further questions after the talk. Let's have a speaker.